I think we're ready now, gentlemen. We did get our talking points a little early Friday night. We've had time to get ready for Professor Wilson's big exam coming up. Welcome, everybody, to the SBAU Astro Hour. Astro stands for astronomy, of course. It's a full 60 minutes at least, and it's all for SBAU, Santa Barbara Astronomical Unit. It's our 276th program, and in your sixth year on the Zoom screen for what is it, June 8th through the 14th. And doggone, we have our own YouTube channel. You can find our website, sbau.org, find out about us, join our happy members, usually on a first Friday up at the beautiful Museum of Natural History behind the Queen of the Missions. This year it's our potluck and it's delayed a week, so it's this Friday night. You got a few days to join the club, $20 a year. Go get the forms at the entrance to the mission and then come join us. It's going to be a great weekend, though. Friday night potluck, Saturday night star party, Sunday afternoon our meeting online to plan things. And the Palmer Observatory will be very busy this summer. And doggone welcome aboard. Here's our hot topics of the week, everybody. For the Astro Hour, big star planets, star-like anyway, that look like stars. Dusk picture and then a dawn shot. Our moon's last quarter occurred 3 o'clock in the morning, apparently. There's a new online app that's going to show us the lunar phases anytime you log in throughout the year. Got a cool photograph from Kitt Peak, the observatory in Arizona, but it's not through the telescope lens. Is it a bird? Is it a plane? Is it Superman? Well, none of the above. Wait till you see it. This week we'll wade through Kepler's 3 laws of planetary movement and then take on Newton's 3 fundamental laws of motion, first posted back in 1687. A lot of math today. Ever heard the term barycenter? Has to do with binary star systems. And how does color and surface temperature in the spectrum, the old electromagnetic, give us the mass of a single star? We're going to learn it. Let's meet the gang, shall we, ladies and gentlemen? Here is our captain of the starship who runs the show, very distinguished gentleman, President Jerry Wilson.
Hi, good morning. My hand disappears. It thinks it's the background. Good morning, Joyce. Good morning, Riley, and good morning, Calvin.
So good morning, Pat Porgy, his beloved wife, our first lady. Yeah. They're all sitting across from him out of sight in a peanut gallery. And we have our first-rate outreach coordinator for the club who is sitting there with us after all these years. Once again, Chuck McPartland.
Good morning.
Married to our merchandise manager and treasurer, best treasurer we've ever had is Pat. Longtime Westmont College science professor, and for 20 years our newsletter editor, Tom Whittemore.
That must be me. Hi.
That's you, man. He's going to bring potato salad. I'm looking
potato salad, yeah.
That. But you can place your orders for the sourdough anytime you want, I guess. How's Maureen? Does she help you bake the bread?
Oh, yeah. Actually, yesterday when Tim and I and David were at the Palmer with the public, Maureen was folding the bread. She was turning it over. That's what you do with sourdough bread. You stick your hand in the dough and you turn it over every 45 minutes. So, and I baked one of the loaves this morning for our dentist. That's where Maureen went this morning because he loves my bread. And it was a beauty. The loaf was a beauty.
Who's your dentist?
Dr. Ciani, Paolo Ciani.
Oh, don't know him.
Yeah.
I just heard a story, a science story about some paleontologists or diggers who came up with wine and what's the stuff you use to make bread?
Yeast, a yeast of some kind.
3,000 years old, and they made some new bread with it.
Well, that's probably the article about Ötzi, that Iceman.
Yeah,
they found an active biome still on his body, and they got some of the yeast that was on his body and made sourdough bread out of it.
Yeah, but Chuck, you know the problem? The sourdough was ossified.
Yeah.
That's right, a little BO thrown in. Hey, here's Jim Crawford, our lens expert, the great supporter of the club and the opening night star for December's in-house local members.
Yeah, no pressure, Tim. No pressure.
Oh, no
yeah.
pressure at all.
How to make a guitar and a lens or a telescope at the same time.
Yeah, Tim was mirrors, not lenses.
That's right. You know, we start every show and we're loving this part because it gets us off in a good mood with Jerry's forwarded silly science cartoons. And we had almost a half a dozen, including Brewster Rocket and
We have exactly half a dozen.
Yeah.
exactly. Okay. Let's scatter these around on screen and have some fun here to start the hour with some levity, if you will.
Yeah, just let me get things lined up
Take
here.
them as they were sent to us, the scientific method. Let's see. Nope. We're going into space. Was that Brewster Rocket
Yep.
inside a turning space station?
Yep.
Okay, Mr. Prez, you want to tell us what's going on? Apparently they're monitoring Mars rovers right there in the
Yep. Can you read the name on the side of the space
Yeah,
station?
it's cute. Are you serious?
Oh, you're kidding. Is that right? All right, what's it? NASA
The guy says rovers Perseverance and Curiosity are still sending data back from Mars. Ever wonder if the Mars rovers get jealous each other or competitive? Maybe even try to sabotage each other. They're just machines, of course not. If they're not subject to the selfish they're not subject to the selfish pettiness of humans that humans are prone to. And here they are on the surface, and it says, look at what I found. It may be evidence of life. And hey, are you trying to disconnect my batteries?
Yeah.
You know, I read that, but didn't read the last one, I swear.
Oh, that's the clincher.
Yeah,
It is, you're right.
you're a punchline avoider.
Yeah.
Well, they're nowhere near each other. Okay, this looks like Newton under the tree. Chuck, you want to guide us through what's going on here?
Well, Newton's sitting under his apple tree, and he's using his tablet here to ask a question of AI if it had existed at his time. He says, "Hey, AI, why does an apple fall to the ground?" And the AI says, "Let me give you a no-fluff answer with an analogy, spelled wrong. A crow doesn't fall because it has wings. An apple falls because it doesn't have wings. If you'd like to know more about crows, let me know." Sounds about typical.
Yeah.
Okay, here's a nice simple one. You want to make sense of this, Tim Crawford?
I'll try. I don't get this one too much.
The real scientific
Guy just
method.
standing there, and then all of a sudden he has a little smile, and the data says no, and he
That's all you
frowns.
need.
Yeah.
That's what
He
it takes.
is a theorist. And this is the experimentalist coming up from the lab, and he goes, no. So it's back to no.
Who do you give credit for that cartoon? Is that a Bizarro?
No,
Mm-mm.
That's not Bizarro. Okay.
I didn't clip that in, so I didn't know.
Who's
XKCG or something like that.
That's
the
this one, yeah.
Tom, you're an astrophotographer, aren't you? You want to make sense
Well,
of this one?
not really, but I did work at Westmont, using images of stars and stuff. It says,
This is blown out, so it's going to be hard to get the.
Well, let me take care of that.
oh, yeah, because there was a splash of sunlight on the floor.
Yeah.
Oh, yeah, it's coming through the window. But we don't know which way it was going. It could go to either table, couldn't it? Bottom line, I guess it was saying that astrophotography specialists are heavy on awnings and table umbrellas and things like that, aren't they?
Yeah, I'm not sure if I even got this one.
Well,
There it is.
So somebody explain it to me then.
so he's saying, let's take the far table. The closer one will be in the sun soon. It's showing the sun shining through the window, and as the day progresses, that brightness is going to move across the floor. So he's suggesting they take the one that's going to stay in darkness.
Oh, I see.
Yeah, I get astrophotographers, meaning that astrophotographers they're really aware of where everything's moving.
Yeah.
Yeah, so astrophotography gives you exactly one extremely minor superpower.
Yeah.
That is to know the sun moves.
On the one hand, we don't want to get melanoma. On the other hand, we got to make our D3.
Yeah.
So I don't know.
This is
Okay.
bad.
Are we coming up on the 100th anniversary of the invention of rubber bands?
Apparently, according to this cartoonist, Larson.
This is a repeat too.
Oh, is it?
Yeah.
I remember seeing this one when I lived in Tucson.
It's new to me. It's funny as hell. Says,
It says on October 23rd, 1927, 3 days after its invention, the first rubber band is tested.
twing.
Yeah. And Ron, if you were to freeze that rubber band, okay, and put it on your kitchen table, what will it do?
Well, I know what it did on the Challenger spacecraft. They called it an O-ring.
When it gets cold, it lengthens.
Yeah.
Oh, it does?
Yeah. And when
Oh, I didn't know that.
And when
Yep.
it warms back up, it shrinks. It goes the other way from most materials.
Right. That was the trick question.
But
Oh man, I didn't know that.
but we didn't have rubber bands before 27, but we did have tires, didn't we? Just not made into little loops.
So anyway, this one says evidence for liquid water on the surface of a terrestrial planet in the habitable zone. It's a paper. We can't see the details, but it's got some illustrations here showing the water and
Yeah.
showing people doing it. And planetary science journals have asked astronomers to please stop submitting their vacation photos.
Pretty good.
There's this scene in Interstellar when Matthew McConaughey's out of his spaceship and he's wading in the middle of the ocean. He's wading, what, knee deep before the giant tsunami
Wave comes
overtakes.
in.
Remember that from Interstellar?
Yes.
I never saw it.
Not a very deep ocean.
No, it was very shallow. That was a great movie. It illustrated time dilation
Yeah,
near massive objects and for a fast spacecraft.
All of the plot premises to set that up was pretty lame.
Yeah, that's what I thought. Anyway,
here we go. A lot of math, Ed, get ready.
Oh, this is the night sky.
Well, we're going to do some math at the end. Here we go.
Yeah. So I can say some things about this.
go ahead.
Every evening, Maureen and I have been going out looking up for the planets, Jupiter and Venus and Mercury. We see easily. We have a really good view to the west. Okay, and last night, Venus and Jupiter were side by side. So I just stuck up my index finger at arm's length, and I noticed that fit right in between Venus and Jupiter. So they must be about 2 to 2.5 degrees apart last
Yeah,
night.
1.9 degrees.
How you like that, Jerry? A finger. I'm an experimentalist.
Well, I guess it depends on your finger.
Yeah. The other thing that's really pretty is we're seeing the descent of the top of the winter hexagon, but you could still get in our sky, we can see Capella on the right, Procyon on the left, and Castor and Pollux well up above. So you can see the last of that beautiful piece, of clockwork. Okay. And Mercury's clearly visible, easy to see, and Venus and Jupiter just spectacular. Okay.
Yeah, they're very bright.
Yeah.
For Mercury, you still need a really good western horizon, though.
Yeah, which we have. Yeah. So it's really, really, really beautiful.
But from my house, this is about how dark it is at 9 o'clock with a slight light at the horizon.
Huh.
Yeah.
Is it my understanding, gentlemen, that the planets look like stars without a telescope? They're part of the pinpricks, but they never give you spikes like stars do?
Stars don't give you spikes unless you have astigmatism or cataracts.
I've got those.
I've
Baron,
seen them in the pictures.
it's the telescope that gives you spikes.
Yeah.
Is that what it is? Well, can you get a
Okay.
spike on a planet in a telescope?
Yeah.
If
So
you
this is
take-
tonight. This is
Take
tonight,
it
right,
with a
Jerry?
wide enough field of view.
Yeah.
Okay.
So, yeah, so this is tonight, but last night Jupiter and Venus were side by side. It was really pretty.
Yeah.
And they're closer tonight.
Mhm. They're not going to be really close, right, Chuck? I mean,
1.6, I think.
okay.
Yeah, what altitude are those at? Because I think I have a hill that'll block that.
Yeah,
Depends what time you go look, but
Yeah.
they're high.
Wait long enough and the hill will work.
Yeah.
Well, how do you measure altitude? It's done in degrees, isn't it?
Yeah.
But you can select the object and then it'll tell you in a planetarium program. It'll
Yeah.
show you the altitude. I'll do that.
So
Yeah.
this is about 3 moon diameters in the night.
Yeah, and I figured it was about the distance and angle between Merak and Dubhe in the Big Dipper, something like that. So I was figuring around 2 degrees.
Okay.
Yeah.
Yeah, that's about right.
Okay.
That's
Spectacular.
Okay. And this is the pre-dawn or the dawn sky
Mm-hmm.
with Neptune, Mars,
Saturn.
and Saturn. Yeah.
Oh, Saturn's there. Oh God.
Saturn's right on the line, and I keep going right over it, thinking it's a star.
Mm-hmm.
So
That's going to be a while till it rises at night, huh?
Oh yeah.
yeah.
September, maybe.
Yeah.
Oh man. Oh
You see,
God.
Mars is in Aries, and it was really fun yesterday. We had people coming through the Palmer, and I had the software set, visible that shows where the sun is in the sky. And the sun is actually in Taurus right now. And I asked somebody, what's the date? And they said, June the 7th. And I said, if you were born this day, what sign would you be in? And they said, well, Gemini. I said, well, looks where the sun is. It's in Taurus. And I just said something about the wobble of the earth, and
Yeah.
they knew about it. They knew about it.
Well, Taurus is April, isn't it? As far as the sign.
Yeah, but everything has shifted by one sign,
Is that
since
right?
since the astrologers tried to confuse the world.
The giant guitar about to eat Tim Crawford from behind.
There's if you see it there, that's my latest creation there.
Well, where'd you put the lens?
Yeah.
Oh, yeah.
Pretty.
Okay.
Here's a picture of Venus
Oh, that's neat. Look at the
and
moon.
Jupiter in March 2023.
Wow.
And it said on June, this is from space.com we're looking at. Jupiter and Venus take a close approach in the evening sky. Let's see if they
Wow.
give the distance there at that time.
Did they occult
They
each
say
other?
less than 2 degrees.
Mm-hmm.
Where do you, boy, you got fast eyes.
Right
Yep.
in that paragraph right above the ad. Right. Come down. Right there.
Oh, yeah. Okay.
Wow.
Nope, no photographs. I want a photograph of what it's going to look like tomorrow. So,
Yeah, look at the moons of Jupiter. Isn't that pretty?
Yeah, that was something else.
yeah.
Right there.
Yeah, they got all
That's
four.
a nice shot. That's a nice shot.
Yeah.
Looks like a refractor too.
Mhm.
Yeah.
Yeah.
Let's get rid of that. Let's get back to this. Okay.
And yesterday, despite the cloud out at the Palmer, it's like the first hour, we still got 55 folks.
Yeah.
And that's
Yeah.
where we were. So now this is a posting from,
We're not seeing it, Jerry.
and see what I wrote
It,
about.
it
what
says
this-
you've started. There we go. There it is.
Okay. So when is this?
Morning.
Yeah, morning, June 12th.
Oh, June 12th. There it is right there.
Yeah.
Yeah. So this is what, Thursday or Friday?
It'll be Friday.
Yeah, Friday. So this is the last quarter moon, even though it looks like a crescent.
Mm-hmm. Yeah, and there's the two major stars in Aries up there.
Yeah. Sheraton and Hamel,
Mm-hmm.
Dorothy's star. If you remember the now this is just a neat opportunity. It shows the it's a piece of software that's available to anyone.
Mm-hmm.
So if you go to this website that's in here,
Actually, a much better one is to go just direct to the NASA Scientific Visualization Studio. But this way, somebody gets some clicks.
Yeah. Oh, no, I happened upon it and played with it for a while, and it's pretty cool.
Yeah.
If there's another one that's pretty cool, go to that one too. But this one, if you take a screenshot real quick, you can get this the address for it here. So
So we're looking at a live shot of the moon
No,
constantly?
no, this is a photograph, but it's a map. It'll show you the phase of the moon. You put in the date. See, the time is June 7, which was yesterday, at 1400 hours Universal Time. So you can figure out what time it is in Greenwich Village, in Greenwich, England,
Greenwich Village.
and then put that in, and it'll show you what you're going to see. It corrects for libation and yeah, libation.
libration.
Yeah.
Libation would make you see a double moon.
Depends how much live you did.
Yeah.
Okay. Now this one I put in.
Oh, that's
I
pretty.
don't think it's in the talking points.
Yeah, I think it
Oh,
was.
yes, it is. It's beautiful.
Okay. Yeah,
Ah.
it was taken from Kitt Peak.
Yeah.
And this is a meteor, which sparked its interest. But I put it in because it shows this arc of
Yeah. In Orion.
velocity around Orion. And
Yeah.
someone asked a week ago or 2 weeks ago, what does Bernard's Loop look like?
Yeah, that was me. Yeah.
This is Bernard's Loop, and you see it's much bigger than anything you'd see in here.
Yeah.
So this wide angle view captured it very nice, very nice.
Yeah. I've spent nights up there, you know.
Mhm.
And the sky is still spectacular despite, Phoenix on the horizon.
That's probably it down there.
Yeah.
I think you'd be looking kind of west, right? Unless it's coming up.
Mhm.
That could be Orion coming up.
No, because then it would be leading with Rigel.
Okay. So
This
that's
is,
going down. So that's southwest.
Yeah, this is
Okay.
June 5th.
Yeah.
Okay.
Well, you can't see this with a naked eye, can you?
No.
Uh-uh.
Are we looking through a lens?
It's a
Well,
camera.
yeah, camera
A
lens.
camera.
Yeah,
So the camera gave us that.
In a
Well,
long exposure too.
yeah. They set the camera up, point it in a certain direction, and leave it on for like say a minute or 10 minutes.
Yeah.
This is going to be 10 or 20 minutes to get this.
So
And
it had
they
to be
hope
tracking too.
Mhm.
yeah, and then that would be tracking. And
Right.
then this was superimposed on the tracking, because if this is fixed, then this is blurred and vice versa.
Okay.
And they hope to capture meteors, and they got a real spectacular one here.
Right. It's over in Canis Major. You see Sirius there?
Yeah.
Yes.
Pretty.
But the fact that it's pink, does that make it hydrogen or oxygen?
Hydrogen.
Hydrogen.
Wow.
That's an amazing shot.
Yeah, it's very nice.
There's another meteor too, right above the dome on the left.
Yeah, I saw that.
Take them both back and you get the epicenter, huh?
Yeah.
You know, there's a feature up here that keeps attracting my eye, and I keep thinking that's a meteor, but it's not. It's just a series of stars lining up, an asterism.
Well, we don't see that many stars in the sky here, that's for sure.
You got to go to Utah.
Wow.
Okay.
Okay,
Okay.
here we go.
Get out your notepads.
Gotta obey the law here, everybody.
So
It's
Johannes,
it's
Go ahead.
blown out. So if you're going to use
Oh,
that
oh, okay.
illustration, yeah.
Thank you.
Gotta adjust our angles.
Yeah. Yeah, when Tim told me last week that Jerry's going to do the central force problem, it just brought back wonderful memories. When I studied that at Purdue, it's just so beautiful. So the most elegant physics is in this stuff.
I did well in plane geometry. I kind of lost it a little bit in non-Euclidean, and Algebra 2 gave us the damn double.
Well, this has nothing to do with Euclidean or non-Euclidean.
Right.
This is there was a guy, Tycho Brahe, whatever you say, and the king of Denmark gave him an island called Uranometria, And he set up a giant quadrant on that, and he was a dedicated, obsessively dedicated observer. And
Actually, Uraniaborg was the name of his observatory,
yeah, okay.
but the island was called Havain,
Uh-huh.
and there's a bad joke about that. That he
Go ahead.
took all his data while he was observing at Havain, and then he moved to Czechoslovakia
Prague.
to Prague, and then he died. But Kepler managed to use his data to come up with these laws, so it was a good thing that he didn't die in Havain.
That's pretty. That's great.
Right.
Well, as Chuck pointed out, Tycho had this, he was the most accurate set of data on planetary positions.
Right.
And
Mars.
Kepler, and he kept this stuff pretty close to his chest. He didn't pass it around.
Right.
But Johannes Kepler somehow, after Tycho died, he got a hold of it, and he went through it and was looking for patterns that he could describe planetary motion with, and he came up with his 3 laws of motion. And this was in the about 1600, early 1600s. So this was what, 500, 600 years ago. And his 3 laws are empirical observations. They do not explain any of why something happens. They're just explaining the patterns in it. And this is how scientific information starts, is with empiricism. But he decided the planets move in elliptical orbits with the sun at one focus of the ellipse. And that's shown in this first law here. And this is an exaggerate. The Earth's going around it. The Earth is actually, the orbit of the Earth is actually much closer to a circle, but it's drawn here as an ellipse to emphasize that. Then his second law is that a line segment joining a planet and the sun, that is, say, this line segment right there, going from there to the planet, will sweep out equal areas during equal time intervals. So that when it sweeps out this area here in a certain time, and drawn out here, and you look at how much of it moves in the same time as from here, and it sweeps out this area. So this area is equal to this area. So that means that this area, the thing down here moves fast, and the thing up here moves slow. Great observation. The third law, which is the law of harmonies, is the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit.
Well, everybody knows that, don't they?
So this is the semi-major axis of its orbit, and this is the semi-minor axis. We're more familiar with the semi-minor axis because this is how you rate your secondary mirror in a Newtonian telescope, by how big the semi-minor axis of your secondary mirror is, which is an elliptical shape. But here we're looking at the semi-major axis here. And so that is a mathematical expression for that. This is the sign here, this little alpha is proportional to. So if t squared doubles, a cubed doubles. But you don't know the constant here, you just know that they behave that way.
But old man Kepler wasn't really concerned with gravitational attraction, was he? Like,
No, he was, but he didn't understand it, and he didn't have he didn't work out any particular rule for that. But they did not know what gravity was. That insight came with Sir Isaac Newton.
okay,
And in 1687, he was in London when the plague broke out. And he moved to his estate, I forget where it is, north of London. And he was locked up in there in isolation. And he, I guess, doodled on some paper, invented calculus, and invented these 3 laws. And he also did another one, the law of gravitation, universal gravitation, but we're not talking about that here.
And it was many, many years. I mean, he published in 1687, but he had actually figured it out many, many years before and didn't bother to publish it.
Right.
Yeah.
And Edmund Halley was talking with Hooke in London, and Hooke was saying, well, we don't know exactly what the equations are for this gravitation, but I think it's r squared, but I can't prove it. And then so Halley mentioned that to Newton, and Newton said, oh, I did that a couple of years ago.
Yeah.
And so Halley had to really push him to publish it.
Yeah. He actually did it, as Chuck points out, years earlier, and he did it in 1666. That's when he was fleeing London to get away from the plague, but it got published in 1687. Now, the first law of motion is an object at rest stays at rest, and an object in motion continues moving at a constant velocity in a straight line unless acted on by an unbalanced force. So, satellites orbit the Earth, and they're being pulled on by a force all the time because they're not moving in a straight line. They're moving in a circle around the Earth. So they're being pulled down. So when an object is in orbit, they're actually falling due to gravity all the time. They just are moving so slowly laterally that they can't make the corner. Now, Newton's second law of acceleration, the law of acceleration, is an object. The acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. So this is the famous F equals ma, and your life is defined by this formula when you take freshman mechanics in college in physics. Newton's third law, action reaction, not terribly important here, but this is how rockets work. You throw something out the back end, and the front end reacts from it. They both separate. So anyway, whoops. This shows now what is observed when binary stars are observed. And this is the empirical observation of a pair of binary stars as they would be observed from Earth. This is the center of mass. If there were a star here, then these would be orbiting around it here in exactly the same pattern, but it doesn't matter because this is the center of their mass. And so they orbit each other in a dance that looks chaotic if you look at it wrong, but it's actually moving around this center of mass called the barycenter.
But wouldn't it get screwed up when they get close to each other, when the blue ring gets close to the orbiting red
Oh,
one?
this is a fixed, these things are always opposite the barycenter from each other. So they will never collide. They will never break this pattern on their own. If a third object came through here and passed through without hitting them, its gravitational field would disrupt this harmonic system.
I see.
So so this is when you look at the binary systems, the center of mass of the baryon of the system we just discussed, and the masses of the two stars are M1 and M2, and they're not the same. And R1 and R2 are their respective distances from the barycenter, and they're not the same. But just like two little kids sitting on a cedar seesaw, they have to balance. Let's see.
Yeah.
Can you see this?
We're just seeing the text.
Oh. Okay.
Oh, you had the teeter-totter guys, right?
Yeah.
There. So you can see this.
Yeah.
Okay, so this is the heavy kid. This is the light kid, and this is their barycenter. And if they were to pivot in a circle around this, first of all, they're balanced. So they would act like a binary star pivoting around the barycenter here. And that's all that says, is that the mass of this kid times this distance is equal to the mass of this kid times this distance. Oops.
You know, gentlemen, what you're looking at is one of two things that have disappeared from all the playgrounds of the world. And they're based on Newton's science. They took out
Newton. So that was I don't know where the balance equation comes from.
The torques
That's
equal torques.
what's that?
Torques equal torques. Yep.
Yeah, I was going to say that this is the torque is actually a relation to this.
It's the answer.
Okay,
But
this is just a balance of torques.
Mhm.
my point was going to be in all the kids' playgrounds, they've taken off teeter-totters and the spinning carousels
Yes.
and left us with slides and swings because they're not as dangerous, I guess. You can fall off these.
Yeah, I've seen many of my friends fall off of a circular, one of those carousels that you push and
Yep.
get caught under it and ground up.
They're gone.
Like a badge of honor to survive it with, oh, it's nothing. So the total separation between the two stars is the sum of their distances. A equals R1 plus R2. Now we use those laws that we just discussed. The Kepler's third law for binary stars. Isaac Newton modified it slightly, but it's still Kepler's law.
You got to go back, Jerry, to the
text.
What did you say?
You got to go back to the text.
Yeah, the equations.
Oh, you can't see those.
No.
Okay. Sorry, I did on my machine, but I guess I didn't.
So Newton's three laws have nothing to do with Kepler's three laws.
Newton's three laws are based on Kepler's laws.
Oh,
Kepler came first. Newton looked at him and said, "Oh, that's interesting."
Right. Yeah, Kepler overlaps with Galileo.
Mhm.
They all are overlap with each other. So this is the two masses.
The day that Galileo died, Newton was born that year, 1622.
really?
He was born on Christmas Day. Newton.
Yep.
Well, did the apple from the tree really happen?
There's a discussion about that. I don't know.
I heard it didn't.
But they still have that tree, basically cuttings from that tree
Yes,
propagations from that tree.
Even though George Washington rushed in and tried to chop it down. But,
Yeah.
anyway, so the two masses are are equal to the cube of the distance between the two masses and the periodicity of the orbit. Now, if you use these this is the A is an astronomical unit, M is the mass of the sun, and P is in years. Then, or these are not in units of the sun. Then you will get an answer that is consistent with our solar system. So M1 and M2 is the total mass of the system in terms of the sun's mass, MO. A is the semi-major axis, average distance between the two stars. P is the orbital period, the time it takes to get around that. And so using these things, you get these two equations. And these are two equations in two unknowns. So just from observing the position of the stars around each other, you can derive the mass of each of these stars. So that's how you weigh the stars in a binary system.
Right.
Uh-oh. So
Well, can I ask a silly side question about the orbit of the Earth?
yes, go ahead.
I understand it's not a perfect circle, but has it been pretty much the same orbit, the same oval or circle, if you will, for 4.5 billion years since the creation of the sun?
How precise you're looking. If you the answer is no in perfect sense, but it's if you ignore small variations, then yes, it's been stable for all that time after Theia hit us. But there are minor perturbations to it over time that have that drive the ice cycle on Earth, and I forget what it's called.
Milankovitch.
Milankovitch, yeah, that cycle. So there are very slight variations in the Earth's orbit.
Well, I read or heard that Jupiter came in close once.
Yes. To the orbit of Mars, roughly.
That would have screwed things up, wouldn't it?
It did. It threw out a lot of stuff.
But didn't alter our orbit.
Oh, it did.
Okay, I'm gonna have to close the Zoom meeting because my computer is hung up.
Okay.
So talk
Are you
among
losing it?
yourselves or sign back in.
Oh,
Okay, another surprise.
so,
Okay.
so Chuck, we're not being recorded?
It's
Hey,
still showing recording in progress.
Okay, so we can talk about anything.
Yeah.
AI has struck again.
Yeah, speaking of that, there's a really neat article in the New York Times this morning about how a lot of these people who are promoting AI as speakers at the commencements,
Oh,
the
yeah.
colleges and stuff, they get booed. They
Yeah,
get booed
yeah.
big time.
Yeah, those graduates, they
Kids
know
are,
they're
kids are looking at, hey, I don't have a job once I get my degree, darn it. So,
Yeah, there'll still be jobs for people who check on the AI and make sure it's behaving.
okay.
Back.
He's
So,
back.
Ron, it looks like you are the host.
no,
But then
we
it's
got him back. He's in the lower right
I'm
screen.
here, but I didn't sign in as a host. I signed in as a guest.
Oh,
But-
okay.
But
Okay.
I leave that open, and so I think we'll be able to go normal.
We were just talking about AI, and I have noted that all my telemarketing calls are really good sounding ladies that take about 5 seconds to answer anything I say back to them.
Hmm.
So I'm curious, did we lose the little foreign
In
sounding
your, in
people?
your case, Ron, that might not be AI.
But at least it's people you can understand, even though it's not a person.
Yeah.
It's not somebody in the Philippines or India anymore. All those people are losing their jobs to
Yeah.
AI. Well, can we still go on with your talking points, Jer?
No reason not to.
There we go.
Okay. So
Okay.
this is a view of a simplified case to illustrate that the things are always opposite each other around the baryonic center. And in this case, the barycenter.
Yeah, there you go.
In this case, it's their circular orbits, the simple case of an ellipse.
Mhm.
This is a binary system and they both have circular orbits. You'd think they'd be
It's
in
a po-
ellipses, wouldn't you?
It's a possibility.
Yeah.
Circle and ellipse, they're just special cases of each other, just
Yeah.
modifying some of the parameters.
It's just easier to visualize what applies to that circle applies to the ellipses also. Here they are each on a line that goes through the barycenter.
Mhm.
And here they are in these circular orbits or elliptical orbits. If one were here, then the other one would have to be here because this always says center between the two. And if one is out here, then the other one stays here.
Right.
And yet they're different sizes, they're different masses.
They're different sizes, but this is always
Right.
In this case,
proportional to the
they seem to
sizes.
be equal masses.
Yes, they are, Chuck, they are.
Yeah.
And you
Oh.
can draw a line from one ball to the other ball, it passes right through the barycenter.
Yep.
But they don't have to be equal masses. They can be
Right.
very different, but the patterns will look different.
Then the ellipses would be smaller for the less massive one.
Yes.
Or for the more massive one, I'm sorry.
But their two orbits pass each other in two places, don't they?
No, they don't, because they're never there at the same time.
That's right. They can't be there at the same time. They will never collide and they will
That
never.
much I know, but the line itself, the orbital, the tracks do intersect. They just don't ever happen to collide,
Yes.
but they do.
Yeah.
Wow.
I'm curious as to which law came first, the second law or the third law, because they really look like you can derive if these two masses are equal, then the area of the two ellipses are going to be equal there. I wonder which one he discovered before the other or together.
Well, Kepler's laws came before Newton's laws.
Right.
The
And they were empirical. They were
Yeah.
empirical, keep in mind. So
And he was really big on geometry, you know.
yes.
So
Mysticism too, Chuck.
yeah. So it probably the area stuff probably came first to him.
I would think Yeah, but it's intuitive from this, the area thing really makes some sense.
Yeah.
Going back on that, Kepler almost lost his mom. She was carted away as a witch, and he saved her by putting her in like a laundry basket or something crazy.
Good
And,
grief.
and Kepler also wrote a fascinating story about going to the moon. Okay. I've always wanted to read that. Have you ever read it, Chuck?
I've read excerpts in
Yeah,
it. It's
okay.
weird.
Okay. Yeah. Sound really fascinating. Quite an imagination for a mystic. I always think of him as a mystic.
Hmm.
He beat Jules Verne's version of going to the moon.
Yeah, I forget the name of the book he wrote, but it's fascinating.
Somnius or something like that. It
Was
was
it Chuck?
something somnium.
Oh yeah, The Dream.
Dream.
Yeah.
Yeah.
Yeah, Somnium.
Okay, this is obviously not a dandelion. What are we looking at here, Jerry?
Binary
Oh,
star.
this
Binary.
is a binary star.
Mhm.
This is a central star, and this is one going around it. Now this one's moving too, but when we draw them, we always center one star around it and put the other one going around it, like it was a planet. And this is a concept. These are actual pictures of that star as it goes around, taken by a variety of telescopes at a variety of resolutions. This is the Hubble Space Telescope, which probably has the tightest resolution. This is the Gemini Telescope in Hawaii, and I think there's one in the south too.
Yeah.
Hubble Space Telescope, Hubble Space Telescope. The Keck, which this one probably has the highest resolution, and very large telescope and very large telescope. So this is a L dwarf binary star, and it's showing these different position angles that it's at. Now, in the ancient world, in the 1500s, 1600s, not truly ancient, but old, this is what astronomy was. They didn't know what stars were. They didn't collect the starlight. They did not have telescopes. So they used quadrants to measure the positions of stars. And they figured all this out. We have telescopes, we actually see the positions of stars farther away, and we can use it to determine the same information that they did. But and this is a picture of, I forgot which binary it is. It's in the talking points. But you
70
see,
Afiyuki.
okay. So you see that it starts here at 1825. It goes around here, period of 87 years, goes around here, and it comes up to 1910. So this was observed for an entire 87-year cycle, always centered on this star. They actually both move around the same barycenter. And in this case, well, this moves, so I can't tell where the barycenter is, but that would depend on the masses.
Can I get a clarification? The little red dot, the little red dots are one.
Wait, the point is, this was astronomy. It was positional, and they wanted telescopes, and they wanted bigger telescopes so they could resolve these different objects. Now, you want to know what the red dots are?
They're one star, and the yellow one is the other star.
Yeah, that's right. At any time in 1848, this is the other star, and this is the other star.
Okay.
So these are different observations, and you can see the uncertainty in their position, but they fit this perfect ellipse here.
They could see all that without a telescope?
No, they were using telescopes.
Yeah,
They were.
Yeah.
Oh.
It's the 1800s.
Yes.
Oh, I'm sorry. I thought it was free before. Okay, got
And
it.
this is the end of that era where you did positional astronomy. And with using this is the 36-inch Lick refractor on Mount Hamilton up near San Jose.
Yeah. Used to take my students there, Jerry, from everywhere.
Yeah, and the floor here goes up and down, so
Yeah.
I can always look.
Really?
Yeah.
Yeah. Floor goes up and down, Tim.
Oh my God.
That's why you have such a complex little stairway over there on the edge.
Yeah.
We got to look at Saturn one night through that 36. It was pretty amazing.
Yes.
Yeah.
And
God, that the floor goes up and down is amazing.
yeah, well, one time, one of those observatories that did this, the floor collapsed.
Yes.
It just crashed down to the basement.
That could have been Yerkes.
I don't know which one it was, but speaking of Yerkes,
Uh-huh.
Here
this
it
is
is.
the 40-inch telescope, the largest
There you
operational telescope in the world. And each of these has an F-19 focal.
Yeah.
So again, the point was not to see nebulas. It was actually spectral astronomy started coming in with these. And so these scopes eventually had spectrometers attached to them, but they weren't terribly good at of taking pictures of nebula. And so you
Now,
can
the
see
floor
here.
doesn't go up and down on this, does it?
Yes, it does.
Yeah, I
Oh
think
my-
it does, Tim.
Yeah.
Holy mackerel.
How'd you like to climb that ladder, Tim?
No, thank you.
Yeah, right. So anyway, the common instrument that they used it for was what's called a filar micrometer. This one is by a German company of Gertner, I think it was. Oh no, Chicago, Illinois, Chicago. Gertner Optics. You look in here, there's an eyepiece, and there are two crosshairs in it. And one crosshair is fixed, the F1, and then the other one, you rotate this, and you can read off of the side the rotation angle that these two are at here, and then you can move the micrometer on the side, and it'll move this crosshair, and you can center it on one, and then center the movable one on this one, and then you can read off the separation of it, and then you can figure out the angular separation, and that's how you record the data. All visual. None of this is photographic. No photometry, no imaging at that time. They did start trying to take images of the planets and the moon through these telescopes and a few of the very brightest nebula. The results were horrible by today's standards, but they were achievements. Any comments, questions, corrections?
I've never seen this. I've never seen that. I didn't study I went to your math and the talking points, but this is interesting because one of the reticles is fixed and the other one will rotate and move. So you take a micrometer readings.
Yeah.
Yeah.
And
You see the picture of the micrometer? You can see the little scale on the right.
Yeah. So that's going to give you the distance from
The
each other?
distance that the one of the crosshairs moved.
Okay.
And this one doesn't have a position angle recorder on it. These things are very, very hard to find on the internet. There's a company called Alamar that wants to sell you photographs, and the photographs that are like this are about $36 a piece, but I'm too cheap to buy them, and I'm too honest to steal them. So I went to other sites and stole those. So anyway, yeah, this is a filar micrometer, and some amateurs do that today. It's like wanting to sail across the Pacific using a sextant. You just like to relive the old days.
Jerry, from the data that they get, are they trying to get an idea of the masses of what they're looking at?
Exactly. That's
There
the
you
whole point.
Okay, that's what I'm trying to fit it all together here.
This is 87 years of the data taken with filar micrometers like that.
Okay.
And from this, they determine the mass of a star.
That's
So
how
what
they do
about what about a star that's not a binary?
it.
Then we look at a chart of color, because you can also see the color of a star, an individual star.
Mhm.
And so you have the surface temperature here of the star, which is really the color, and it gives you the luminosity, this type of data, which was developed in the late or the 19th century. And then you can go to this kind of data, which relates mass to luminosity, and you found the luminosity from the color on the previous chart. And you see that this star here has a mass roughly 2 times the sun. So, because these are units of solar masses. So these are from theoretical models of the stars that you get the mass of it this way. But for
Jerry,
a binary star, you get it mathematically.
Jerry, I have a question for you. The luminosity how is that related to the magnitude?
The luminosity is the total amount of radiation that the star puts out in all directions, 4 pi steradians, all, everywhere. Like if you put an eggshell around a star, how much of that heat would it collect, which was all of it, be a Dyson sphere. And then you can figure out if something has that luminosity, because I've done this calculation, but the sun has a certain luminosity, and then you can figure out how much of that luminosity your eye or the telescope is absorbing, because you expand that sphere out to a sphere that's at the same distance you are from the sun. So you know how much the inverse square law has dimmed that star.
Oh,
And then
wow.
much of it you collect, you multiply that area density by the area of your retina or your area of your pupil, and that gives you the magnitude.
Holy cow.
So this is more like the absolute magnitude over here on the left, the luminosity. I mean,
Okay.
more proportional to
Yeah,
that.
this is luminosity in terms of the sun luminosity, but it's the it's the wattage comes out, the energy that comes out in all directions, in all wavelengths.
Well, would your red giants have the most of all stars, or might they even be less than?
No, the white stuff is going to be the most energetic, pouring out the most crap.
Okay.
And this is just a sort of a main sequence
Right.
diagram here, and it's flipped left to right relative to the previous one.
Yes.
Um,
And as Chuck points out in detail, there are other branches covering other types of stars. That was figured out in the early 20th century. This was the type of thing you had in the late 19th century. So this is where our astronomy hobby came from.
So Betelgeuse would have less possibly than a white dwarf?
no,
Mm-mm.
white
That'll
dwarf
never
is a
happen?
whole other section of the diagram. That was just for main sequence stars, Ron.
Oh,
And
I
both
see.
red supergiants and white dwarfs are off of that chart.
So this was the last era of observational astronomy was positional. That's why the telescopes are so long. You needed high magnification and relatively large light gathering power. This is the largest practical refractor built. Above this, you only can support the lens around the edge, so the glass would sag enough that it would distort the image.
Yeah.
In Paris, they built a 90-inch diameter Great Paris refractor, but because of the sag, it was laid down flat in the basement of the Paris Observatory, and so that the gravity would pull down on the side of the lens. And then the tube, which was, I think it was F22 or F24, it was a real long tube, and it was all flat, so you didn't point it around. It had a coelostat, which is a rotating, a movable mirror that pointed around, and you could look at different parts of the sky like that.
Huh.
But the museum or the refractor was generally a failure. It wasn't used. It wasn't good enough, and I believe parts of it are still there in a museum in Paris.
I can remember the opticians the company that made the Yerkes and the other I think the Lick as well.
Yeah, Alvin Clark and Sons.
There you go, Alvin Clark. I couldn't remember it. But
Yes.
I think that's one of the most famous American
It
makers.
is. And they're excellent telescopes. If you can get your hands on, say, a 6-inch or an 8-inch Alvin Clark refractor, those things are worth bank as a
I met a guy up at probably the only RTMC that I went to, and he collected these things, those Alvin Clark refractors.
Yeah.
And he worked at a university back east, and then he was laid off from the university, and he made a deal with them. He traded one refractor that he didn't like for one that was complete to the university, and got a hold of one that he had up with him up at the RTMC. Quite a follow. It was quite a nice talk I had with him about those.
They're achromats, though. They're not apochromatic. So
No, they were,
They're
yeah.
2 elements, crown and flint glass. And they were stuck with this up until the 50s or 60s. And Unitron, the great amateur telescope, made doublets like this, and they were F15 and F16 because that was any faster than that, you get chromatic aberration. And then people like who's the guy that did Teleview? Anyway.
Nagler?
Al
Nag-
Nagler.
Yes,
Al
Al.
Nagler?
He started getting exotic glasses, and
Yeah.
other people did too from glass makers. They started getting using they could tune in the diffractive index, and they were able to make now telescopes all of a sudden that were like F5 and F4.
Yep.
Things that were great telescopes are taking pictures of nebula and faint objects. And today we don't have to put up with these long focal lengths.
Well, photography hit the world about the mid 1800s.
Yeah, 1856, I think, was the first attempt at a telescope view of the moon.
1840 something, I think. Yeah.
Okay, could be.
Wow.
That's when they decided, whoops, wait a minute. Pallas and Juno and Vesta aren't planets.
Oh, wow.
You
But
know,
they never put a daguerreotype on a lens of a telescope.
Yes,
Yeah,
they did.
yeah.
That's how they did it.
Wow.
And they yelled, "Smile!"
Yeah.
And
But hold still.
had the explosion of the whatever that was called. Well, I think I learned a lot. I can't wait for the exam. How about the rest of you guys? You learn anything, Tim?
It was a good one today.
Yeah, you got it. Well, I hope to see you hardcore members at our big yearly potluck on Friday night. Bring an appetite and a covered dish. Star party will follow the following night, and our meeting in the afternoon on Sunday plans things out. We'll see you next Monday morning here on Astro Hour number 277.
Woo.
Thank you on behalf of SBAU.
Yeah, thank you all. Thanks, Jerry.
Appreciate it, guys.
Bye.
See you later.